Good afternoon, everybody. Let's get started. For announcements, take a look at homework 7. That is posted. All of the assignments and let's see, homework assignment 7, homework assignment 8, they're out there. Check out those dates. And then we'll talk about lab 10 more this week. So during the previous class, we finished up IoT, Internet of Things. We talked about connecting your microcontroller and computers to the world using MQTT. And since we're changing topics, I wanted to step back and look at really what drove all of these major course topics. We're trying to connect to the physical world using an electromechanical device or some other physical device, as well as sensors. And we have all of these supporting device categories or electronics categories that I wanted to cover during this course, that we are covering during this course, and that I think are important and common to electronic systems that connect to the physical world and communicate and are powered by something. We're going to stay on the topic of communications by focusing on RF communications. So we're going to start that today. So RF is radio frequency. We're talking about communicating over the airwaves, right, using electromagnetic fields. And so this is a big topic. When you study radio frequency, you can study electromagnetic fields, you can study now communication systems, you can study RF engineering, transmission lines, different types of electromagnetic structures. We're not going to dive deep into those topics, but I do want to give you enough at a system level so that you can speak with those who have studied those levels of RF engineering and RF communications. So I think this will give you a good background where you can start at this high level and then dig down into topics more deeply if you wish. Let's start off with the purpose of an RF communication system. Like functionally, why are we using these systems? So the overall purpose of a communication link that uses RF is to transport information, right? You have information at some point, you want to get that information to another point. And the starting point is your information source, and the end point is your information destination, right? So let's draw a cartoon here with a source and a destination. So the information source might be voice waveforms. It might be music waveforms. It might be analog, an analog output from analog electronics. So we talked about analog versus digital, but you could have information in the form of analog waveforms that you want to get to the destination. And you can also have digital sources. So you might have messages, you might have email, you might have numeric values that you're trying to transport from one place to another over RF. You might have an initial source that's analog, right? Analog values, a signal, but you might digitize those analog values, and that would be a digital waveform or digital information that you want to transport over RF to your destination. So the destination could be analog, right? People, our ears, receive analog, or input to an analog electronics interface. The information destination could be human interfaces, some kind of screen. It could be a computer. It could be controlled devices that need that digital information. And in between, we're going to put this RF system. We're going to put a transmitter, an antenna. We're going to propagate electromagnetic waves. We're going to receive those EM waves via an antenna and then use a receiver to extract that information at the destination. Okay, and so what are we trying to do here? We're not trying to reach perfection, but we do have a measure of quality that we want to achieve. And that overall metric of quality is really this, that the information is received with low enough noise, low enough distortion, few enough errors so that you can do what you need to do with that information at the destination. Okay, so in this generic diagram of an RF system, let's talk about what each part does. The transmitter converts information into a signal that can be propagated over the air using electromagnetic waves. Okay, and that signal is going to be a sinusoid. So it's a sinusoid whose amplitude, frequency, and phase uh, is modulated to represent that information. And we'll talk about modulation and demodulation. Okay, so that transmitter produces that signal. And then there's an antenna to convert the conducted signal power. So this is, I'm drawing this line here as a cable. So that's conducted information. It means there's a voltage and there's a current, that's power, delivered to that antenna. And that antenna is converting that conducted power to a sinusoidal electromagnetic field that can be propagated through a medium, a vacuum, air, typically, something like that, using electromagnetic waves. At the receiver, you have an antenna, and that antenna, the receive antenna, converts that EM field, that modulated sinusoidal EM field, to conducted sinusoidal power, right? Voltage and current that is transmitted or taken from the antenna, conveyed from the antenna to the receiver using a coax cable or some other transmission line, just metal wires, conductors. And then the receiver converts that received sinusoid into the information that you wanted to send from the source to the destination. And you're hoping that that information matches the input to the transmitter. And when I say match, I mean good enough. It gets to the receiver with acceptable quality, with low enough noise or with few enough errors. Okay. And so this is a one-way link here from transmitter to receiver, but if you have a bidirectional link, then you use the same approach in the reverse direction. A transceiver is both a transmitter and receiver, so you could have transceivers at both ends of this link to form a bidirectional link. Okay, so this is a big set of topics here, but here is my approach to covering these topics. So here's that diagram from the source to the destination of information. We're going to cover the basics of RF systems to really answer two important questions that really I think most people care about when they're working with high-level RF systems that communicate information. There are other types of systems like radar systems. You can have radar that detects aircraft in the air or pipes underground. We're going to focus on communication systems in this case. Okay, so these are the two important questions that I'm answering, or I want to give you information to answer, or a background to answer. For a given RF system, over what distance can the information be successfully communicated with good enough performance? Right, so that's one of the questions. The other question is, well, for a given distance, right, you have two places on Earth that you want to communicate between. It could be the over the horizon to another country, or it could be from your laptop to your Wi-Fi router in your house. But for a given distance, what are the major details, traits, characteristics of an RF system needed to successfully communicate the information? For example, what antennas do you need? What kind of antennas? What kind of specifications for the antennas? What transmit power do you need to radiate? What are the receiver specs? How low noise does your receiver have to be? Or what are the the other RF system specifications that you need to successfully communicate over a given distance with good enough quality? Okay, so in talking about these two important questions, we're going to cover these areas. We're going to cover first, representing information using modulated sinusoids. So you have an information source. What does that transmitter have to do to transform that information into a signal that can be radiated over the air? Okay, we're going to talk about the RF frequency spectrum. Right, that's the frequency domain of the signals you're transmitting, and allocation of spectrum. what the FCC in the United States or the government will let you transmit and how that's allocated. We're going to talk about third, the fundamentals of electromagnetics, right? The fundamentals of using EM fields to communicate. And then we're going to look at the hardware. We're going to talk about the functions and the components of transmitters and receivers. Right? What do you need in these boxes here, the transmitter and the receiver, to make certain functions happen so that you can make the system work. We're going to talk about radio wave propagation and path loss, and that has to do with, well, if you have a certain distance between your transmitter and receiver, you know the transmit power and you know the antenna gain, how much power can you expect at the receiver? How does that compare to the noise? So how good is your the fidelity of the signal at your receiver and the quality of the information out of your receiver? We're going to talk about RF circuit performance. We're going to talk about noise performance, signal to noise ratio, 1 dB compression point, output third order intercept point. Okay, so those are common specifications for radio frequency components. And then we'll get to the communications range versus quality. We're going to talk about link budgets. And then finally, we're going to look at RF circuit construction and test equipment, what you would use to test transmitters and receivers and RF components, and even at the communication link level. Okay, so this is a big area to cover, but again, I think we can summarize this in a few lectures so that you get a background really crossing these areas, and these are separate courses, in fact, in electrical engineering. I'm going to introduce and summarize analog and digital communications, communication system theory, electromagnetic fields, antennas, and radio wave propagation. Okay. So we're going to look at that. So let's walk through each one of these areas and talk about them. Let's start with representing information using modulated sinusoids. So how do you take this information source, either analog or digital, these waveforms coming in, these voltages, and convert them into something that could be delivered to an antenna and then radiated? Okay, so sinusoids. I'm sure you're familiar with sinusoids. We've talked about these, but let's define the parameters that I'm going to be using over the next few slides. So here's a sinusoid. It's a voltage waveform. It has an amplitude A in volts. It has a frequency in radians per second, omega, and it has a phase, phi here. Okay, so that's how we're going to define the parameters that characterize a sinusoid. And when we're talking frequency, we will talk in radians per second, but also hertz, frequency in hertz, where F is the frequency in hertz. That's related by this equation, omega equals 2 pi F. Omega is in radians per second, hertz, frequency is in cycles per second or hertz. Okay, so you can represent when I talk about hertz or megahertz, that's what this F is here. Okay. So here is a sinusoid with frequency 100 megahertz, right? This is voltage versus time in nanoseconds. This is what a 100 megahertz waveform sinusoid would look like on an oscilloscope. Okay, and if you increase the frequency, then you get more cycles viewed in that same time frame, because the period is reduced and the period is 1 over F. So instead of cycles per second, you get seconds per cycle. Seconds per cycle is a measure of the period of the waveform, let's say from one peak to the next peak, or from one zero crossing in one direction to the next zero crossing in the same direction. Okay, so here you have a period of 10 nanoseconds, and that's 1 over 100 megahertz, 1 over 100 times 10 to the 6th. Okay. And then there's phase. So the units of phase are generally radians, but we'll often talk about phase in degrees, because I can visualize 40 degrees. I can visualize 75 degrees. it's hard to visualize 0.2 radians, right? So we often talk in degrees versus radians when we're talking about phase angles. So a phase of 0 degrees would look like this. This is a cosine with 0 degree phase. You can tell because at time 0 you have the peak. Cosine has a peak at time 0 for 0 phase when it has 0 phase. If you have a positive phase, let's say a phase of 60 degrees, so phi equals plus 60, that's actually the advance of a waveform. So if you look at the baseline waveform with 0 degrees, the peak is going to happen a little early. So if you have a positive phase, in this case, just let's not wrap around the unit circle. Let's say 180 degrees or less. If you have a positive phase, then you have an advance of the waveform. A delay of the waveform is a negative phase. So minus 60 degree phase is the delay of the waveform. So when I'm talking about phase shifts in communication signals and sinusoids, I'm talking about advancing or delaying that sinusoid. And that's one way you can convey information, by advancing or delaying the sinusoid with respect to a reference. So phase shifts also relate to offsets in time. So if you have a delta phase, delta phi here, you can relate that to delta t, the shift in time, by omega, right? Radians per second for omega times seconds for delta t is radians phase. So those are the parameters we're talking about when we talk about modulating or demodulating waveforms, which we'll talk about next. Okay. So we need to use these sinusoids to represent information, analog and digital information. So when I talk about an analog or digital waveform, I'm talking about a voltage. And we use these voltages to represent something. This might be your voice. So here's voltage versus time, and it might look something like this cartoon. So we want to get this information, this waveform, somewhere else over an RF system. We also might have digital information. So this is a cartoon of a digital signal with high and low values. So this would be a binary signal in voltage versus time. Okay, so RF transmitters, their whole purpose is to radiate sinusoids over the air. And you want to radiate sinusoids that can be detected by an RF receiver, which we'll talk about later. Okay, so we would like to represent information using the parameters of a sinusoid. Okay, and so we'll talk about a little bit about antennas and frequency spectrum, but basically, if you have within a certain frequency range, you have reasonable antennas that could convert the conducted power to the antenna to electromagnetic waves, and there's a frequency range of that sinusoid that results in realistic sizes of antennas, because that's related to the wavelength. Antenna size is related to wavelength generally. And so if when you're carrying around your cell phone or a walkie-talkie, or you're using a satellite dish outside your house, you want a reasonable size, and that relates to the wavelengths that we'll use. And wavelength relates to other things like propagation characteristics, but the point here is that RF transmitters radiate these modulated sinusoids over the air that convey information to a receiver. So we're going to use amplitude, frequency, and or phase, so one or more of these together, to represent the analog or digital information. So instead of the sinusoid that I introduced, that I said, well, it has an amplitude, a frequency, and a phase, right? Instead of that time domain waveform, we're going to vary the amplitude and or frequency and or phase over time according to the information. So that information is going to change amplitude, frequency, and or phase. So that process of varying the sinusoid's amplitude, frequency, and or phase to send information is called modulation. So when anyone says modulation with regard to RF systems, they mean you're taking information and you're changing these characteristics of the sinusoid. You're using that information and encoding it on the sinusoid's amplitude, frequency, and or phase. That's what modulation is. It means this kind of disturbing those values in a way that conveys information. And so when you have a receiver, the process of recovering the information from the sinusoid's amplitude, frequency, and or phase is called demodulation. So you have a sinusoid, it has encoded information on it. You want to get that information out. That's called demodulation. The different types of modulation you might have heard of are amplitude modulation. So amplitude modulation is, well, when you modulate the amplitude, that means take that amplitude and vary it with time. So you might take that analog waveform and depending upon its values, change the amplitude of this cosine. Right? So that's why it's A of t, and frequency might be fixed and phase might be fixed. Then there's frequency modulation. Frequency modulation would look like this. I have a frequency that changes with time. So you might have the amplitude of your information signal change the frequency of this frequency modulated signal. All right, this frequency modulated sinusoid. And then you have phase modulation. So you could also take characteristics like the amplitude of this analog signal and have that change the phase. Right, so that information is being encoded or used to change the sinusoid. Okay, and these are all used for, they have different characteristics. They have different applications. For example, AM is used for air traffic control communications. It's good for your ear, like the human ear can actually pick out very weak signals when AM is used. So you can be far away from a weather broadcast or an air traffic control transmitter and just pick out the information that you need. But the fidelity never seems really super great when you're when you want let's say high fidelity, good fidelity music over, let's say, FM radio. So it's FM. You can use FM, but FM, when you get a very low signal to noise ratio at the receiver, you tend to get nothing. There's a threshold effect where you get very bad quality of sound if you don't have a strong enough signal. Okay. And then phase modulation is often used in digital systems. In fact, you can use phase modulation and amplitude modulation at the same time to fit a lot of bits, a higher bit rate into a modulated signal. Okay, but the big takeaway here is transmitters modulate a sinusoid to send information. Receivers demodulate a sinusoid to recover information. Okay. And that sinusoid has a special name. We call that sinusoid the carrier. The sinusoid that's carrying this information is called the carrier. So if you have a modulated carrier, you're changing the amplitude, frequency, and or phase of that carrier, that sinusoid. Okay. And there's some specific uses of the word carrier that I won't get into. The carrier can actually look like it has disappeared from the modulated signal for certain modulations, but we'll leave those details for later. Okay, let's give some examples of modulation. I want you to be able to visualize what is happening here for analog and digital waveforms that are modulated. Okay, so let's talk about modulation of analog signals. And we'll start off with showing the modulating signal. Okay, the modulating signal is the information you want to represent with the sinusoid. And the modulated signal is the signal representing the information. So the modulating signal modulates a sinusoid to result in a modulated signal. Okay, so for AM, let's imagine you have a voltage versus time that looks like this. It might be a small snippet of a voice waveform, music waveform, something like that. Well, what you're doing with this waveform, typically with AM, is you're changing the amplitude of the sinusoid. Okay, so for visualization here, I have exaggerated the carrier frequency versus the modulating signal frequency. Ordinarily, if you were looking at an AM information source, an analog source, this modulating signal, and you show it on the same time scale uh, as the modulated signal, it'd be hard to visualize the change of the amplitude or change of frequency or change of phase. So I'm exaggerating a little bit here, but the principle comes through. So here's the amplitude of the modulating signal, and you can see how the amplitude of the sinusoid, this carrier, it changes along with the information signal, the modulating signal. Okay, so you're modulating the amplitude. If this voltage were just a constant, then this sinusoid would just have a constant amplitude. It would not change versus time. Okay, and then there's frequency modulation. So let's take that same waveform, voltage versus time, and as the amplitude goes high of the modulating signal, then we're going to have the frequency go high of the modulated signal. And as the amplitude goes low of the modulating signal, we're going to lower the frequency, the modulated signal. So this is frequency modulation. You can see here the frequency gets high at the peak here, and then the frequency gets low at the trough here. Okay. And again, I am exaggerating the relative frequency content of modulating versus modulated, so you can see the detail of the increasing frequency and the decreasing frequency here. For phase modulation, if you have the same waveform, this is what phase modulation would look like. So what I'm doing here is I'm showing, I think the gray is an unmodulated reference against which you can compare the blue. So the blue is the modulated signal, and you can see as let's see, as the voltage goes high, the phase gets advanced a little bit. And as the voltage goes low of the modulating signal, the modulated signal's phase gets delayed a bit, right? And so if you could track that phase, if you could extract the phase of that blue signal and plot it, you would see the phase follows this characteristic of the modulating signal waveform. So these are these three modulations: amplitude modulation, frequency modulation, phase modulation for analog signals. Let's take a look at modulation of digital signals in the same way. So here's the modulating signal and the modulated signal for amplitude shift keying. Okay, so here you can see that you have highs and lows, this binary signal, and I have a representation of the modulated signal. So when you have a high voltage, you have a high amplitude of the sinusoid. A low voltage, you have a low amplitude of the sinusoid. Okay, so there's different types of ASK you could use. This could also be 0 volts, which would be on-off keying. But I wanted to show you an example of amplitude shift keying that had non-zero amplitudes here. If you show this to an expert in communication systems, they're going to say, well, that digital waveform shouldn't really be perfectly square like that. Usually we shape the modulating signal so we don't have these sharp transitions, because sharp transitions in a modulated waveform actually occupy a wider bandwidth unnecessarily. We're not going to worry about that now. This is just for visualization purposes, but know that when you really have a modulating signal, you apply that directly to a sinusoid, typically there's some pulse shaping, so you don't have these very sharp transitions that spread the width in the frequency domain, which we'll talk about, wider than necessary. Okay, so that's amplitude shift keying. You can see how that relates to AM for analog signals. Frequency shift keying relates to FM. And here I have a voltage versus time of some digital binary information, right? High and low bits here. And when the voltage is high, the frequency will be high of the modulated signal. When the voltage is low of the modulating signal, the frequency is low. So we're actually switching between two frequencies here. So you can detect the frequency at the receiver and tell if the signal should be high or low at the output. Okay. And here's phase shift keying. So again, with this extreme example of rectangular pulses here, highs and lows, these binary bits here. So here, what I'm doing is I'm shifting the phase based on whether the value is high or low. So you can see here I have a nice clean sinusoidal waveform, and then the bit changes. So I change the phase all of a sudden, and the bit changes, the value changes. So I change the phase all of a sudden. Again, generally you don't want to change the phase that rapidly, but for illustration purposes, this works. Right? So this gets the point across that you can use amplitude, frequency, and phase to encode that information on a sinusoid. Right? Okay, so that's how you represent information using modulated sinusoids. Let's go on to the second subtopic, the RF frequency spectrum and allocation of that spectrum. So what we're talking about when I say spectrum is the signal or RF signals in the frequency domain instead of the time domain. We were just looking at time domain waveforms, right? Some value versus time. When we talk about the frequency domain, we're talking about some value versus frequency. And I think for a long time, we've all generally understood that RF signals occupy different frequencies. So whenever you tuned in a radio station, 97.3 megahertz or 94.1 megahertz or 98.5 megahertz or 850 kilohertz, if you listen to AM radio, you kind of understand, well, these are differentiated from each other in some way, and that some way is frequency. So you probably have also heard, you've seen your router operate, you can set up two different networks on 2.4 gigahertz or 5 gigahertz. So those are two different frequency bands that you can use. And in aviation, since we deal with aviation in lab, you have frequencies here, 118.825, that's the automated weather broadcast from the Boulder Airport, and 122.725 megahertz, that's the common traffic advisory frequency for Boulder Airport. So you see frequencies, we all kind of, we see these RF frequencies show up in our life, and they give us this idea that, well, RF signals convey information, then they occupy different frequencies. So this understanding that we've seen our whole lives since we've used a radio, an FM radio, this understanding helps us grasp the concept of frequency domain representation of radio frequency signals. So taking the Fourier transform of a time domain signal lets us visualize the signal in the frequency domain, and we call this frequency domain visualization the frequency spectrum. And so mathematically, this is the Fourier transform. If you want to take the Fourier transform of V of t, you do this, right? This is the way you represent the Fourier transform of V of t, and you get V of f, capital V of f here. So V of t is a waveform like this. This is time domain. It has a t in it. A cos 2 pi fc t plus phi is a time domain waveform because it changes with time. Right? You could plot it versus time. In the frequency domain, we have some value, which is this capital V of F, or the Fourier transform of V of T. We're saying that is some value versus frequency. We're looking at how the signal occupies the frequency domain, the frequency space, instead of the time domain. And so in the frequency domain, if you have a 100 megahertz signal somewhere in the FM radio band, right, that would show up at 100 megahertz in the frequency domain, in the spectrum. So whenever I'm talking about the RF spectrum or a plot of the RF spectrum, I'm talking essentially about the Fourier transform or a frequency representation where it's some value versus time. It could be, it could even be power versus time representing the spectrum. I'm sorry, messed that up. Power versus frequency. It's the frequency spectrum is something versus frequency. So even power versus frequency. It's showing occupation, how the frequency bands are occupied. So let's talk about a little about the RF center frequency and bandwidth. So measurements of the frequency spectrum, they show RF signals operating at different center frequencies. So here is an actual measurement through an antenna using a spectrum analyzer of the broadcast FM band. And I'm pretty sure that was probably in Boulder or Longmont, somewhere around here. But you can see the frequency spectrum received from the antenna. So here's a measure of power, right? So this is power in a certain bandwidth in a certain unit, but that's the strength of the signal versus frequency. And so frequency here goes from 85 megahertz to 110 megahertz. So you know, if you get in your car and tune around in the FM band, you go from just above 87 megahertz to just below 108 megahertz, and these are all the radio stations. Okay, these signals are separated using different center frequencies to operate at the same time without mutually interfering, right? So this is KOA right here, 94.1. This is KBCO, 97.3. This is KYGO, 98.5 right here. Those are the center frequencies in megahertz. And so at the same time, if you look at the output of your antenna, all of these signals are coming out on top of each other, summed together all at once. They all interfere with each other, right? If you just look at the whole spectrum without filtering out one of those signals. So at the receiver, signals are selected using filters so that only the desired signal is demodulated. So somehow you have to extract only one, like this green boxed signal here. You have to extract only that to demodulate it. Otherwise, you're just getting this mix of signals going into the demodulator. It won't work. But a point here is that you can separate these signals in frequency so that you can have shared use of the electromagnetic spectrum. So this spectrum shows the strength of each signal, and in this case, this is the power of the signal within what we call the resolution bandwidth for spectrum measurement. So resolution bandwidth is a setting on a spectrum analyzer. A spectrum analyzer is it's sort of like an oscilloscope, except an oscilloscope shows you signals in the time domain. A spectrum analyzer shows you signals in the frequency domain, right? Power versus frequency. There's a setting called resolution bandwidth that shows you how wide is the bin for each point on the plot in which to detect power. Okay, so each signal has a non-zero bandwidth due to modulation of the signal. If you take the Fourier transform of a sinusoid, you get a delta function. It's just infinitely narrow and infinitely tall, but when you modulate a signal, you actually get a non-zero bandwidth. It widens out. And the bandwidth of each modulated signal depends upon the bandwidth of the modulating signal, like whether it's voice or some maybe higher frequency signal, and the modulation type. Is it AM? Is it FM? And some parameters that go along with those modulation types, like modulation indices. But the point here is that um, signals take bandwidth. They are not infinitely narrow. They're not zero bandwidth. And the wider bandwidth or a higher data rate of a modulating signal typically results in wider bandwidth of the modulated signal. So when you're trying to send data faster, it typically takes more bandwidth. Okay, there's some more bandwidth efficient modulations than others, but generally for the same modulation, if you increase the rate, you're going to get a wider bandwidth occupied by the RF signal. And bandwidth within a given geographical region, let's say your hometown or Boulder, is a finite resource, right? So here's the FM band. You can't put infinite radio stations in here, right? Because each radio station takes up a finite bandwidth. There's only so much of the band you can use for radio, for FM radio. So it's a finite resource. So it all has to be managed. Okay. So that's where frequency allocation comes in. So the RF frequency spectrum is allocated to licensed and unlicensed users. So if you have an FM radio station, you have an authorization, a license to transmit. If you have a Wi-Fi router in your house, you're an unlicensed user, and that part of the spectrum, the frequency spectrum, has been allocated to you as an unlicensed user. But you cannot just go transmit anywhere in the spectrum with any kind of waveform without some kind of authorization. And in the US, the Federal Communications Commission, the FCC, regulates RF spectrum usage. Okay, and the FCC issues licenses and special authorizations, and there's different kind of licenses and authorizations to commercial users and to private users. So if you're a commercial radio station, then you have a license issued to you to use that portion of the spectrum. If you're a research organization, you can get some kind of experimental license to do some experiments, even though you're doing it for hire as maybe a commercial organization. Private users like amateur radio operators get a license, and you're authorized to transmit in certain bands. Okay, and this all can be seen on an allocation map. So this is a US in the US, a frequency allocation. I think this is back from 2016. This is a big poster. But you can see at the lower end, this is 9 kilohertz. That's a pretty low frequency. And then you go left to right here and then jump down. This would really be one long wide strip, right? So here's 9 kilohertz up to some frequency, and then jump down a row, and you can see you keep going up in frequency. So here's 300 kilohertz to 3 megahertz, 3 megahertz to 30 megahertz, and so on. 30 megahertz to 300. So this table this plot goes all the way up to 300 gigahertz. That's pretty high frequency. And you can see there's nothing unallocated in here. The spectrum is allocated, so you have to fit into one of these categories in order to have authorization to transmit, either licensed or unlicensed. Okay, if you break away the spectrum that I was just showing you, or a little wider than that, this is between 50 megahertz and 137 megahertz. You can see, well, there's amateur radio bands, amateur radio operators can transmit down here. Broadcast television here. Still, there's digital television, still broadcast. Here's the FM radio band from 88 megahertz up to 108. So that's FM broadcasting. And that spectrum I showed you fits in here. Aircraft navigational aids, VORs, etc. They fall in the 108 to 118, and then aircraft communications 118 to 137 in there. So the spectrum is allocated. And when we talk about the allocation, you go back to the previous slide, those signals that have finite bandwidth have to be at the right center frequency, and they have to also comply with certain bandwidths, instantaneous bandwidths. Okay. So this whole spectrum is broken up into different bands, and you're going to hear these if you work in a company that deals with RF systems or antennas or, you know, um, really anything that transmits or even anything that can radiate emissions, electromagnetic emissions, and you have to keep those emissions low. You'll hear these names of the RF bands. So you might have heard of VHF. Everybody's heard of something like VHF, RF, radio frequency VHF. That's actually a range, according to the ITU, the International Telecommunications Union. It falls between 30 and 300 megahertz, according to them. UHF between 300 megahertz and 3 gigahertz. There's SHF, EHF. You can go low in frequency, VLF, LF, MF, HF. HF, which stands for high frequency, these days is a pretty low frequency actually, but back when radios were first being developed, HF was pretty high in frequency. The name stuck. So if you hear VHF, now you know what we're talking about, but there are other names for these bands depending upon the organization. So the IEEE has these bands that were really radar based. They came from old radar terms that went back to World War II. You still have HF, VHF, and UHF, but you have L band and S band and C band and X band, KU band, K, KA, V band, W band. Okay, so these bands have names. So if you hear the bands, you might not memorize the frequency range, but you know that it's a band and it corresponds to some frequency range. And these two tables, they conflict with each other. You can see here, this is the IEEE designation up top and the ITU designation at the bottom. You can see VHF doesn't exactly overlap. UHF definitely doesn't overlap. And then you have these higher radar designated bands typically, although we do use those for communications. You can have an S-band communication link. It's not necessarily radar, but someone might say, oh, that's a UHF band, and someone might say that's L band, and they mean the same thing. So I wanted to point that out so that you know you don't get confused if you hear those. And frequencies and names, or the frequency ranges and names for these bands might differ for different organizations and different contexts. So, and there are also other band designations for these ranges that go above and below the ITU frequencies, but I'll leave those for your own research. All right. Okay, so we talked about spectrum. I want to say a little bit about not the frequency axis, but the power axis of spectrum. Power ratios are often stated in decibels. And so you can actually state absolute RF power and relative RF power measures in decibels as units. And there's a reason we use dB. Decibels, when I say dB, I mean decibels. So dB actually allows you to express a very wide power range using a narrower range of values. So you can express a femtowatt to a megawatt using a reasonable range of values when you use decibels. So the values in decibels, they always express a power ratio. The point of decibels was to express a power ratio. You might talk to some people who have other beliefs about this, but if you look back, when we were talking about bells and decibels, it's really a power ratio. Although you can express voltage ratios, but it gets a little confusing. I'll show you that in a bit. But a power ratio in decibels is this: 10 log base 10 of two powers. You're expressing a ratio of power 2 versus power 1, or power 2 compared to power 1. Okay, and it's a decibel because of this 10 out here out front. A bell, which we never use, would be just log base 10 of a power ratio. We typically use decibels, which is 10 log 10 of the power ratio. And so, an example is that RF amplifier gain is typically expressed in dB, decibels. Right? You typically don't use voltage ratios to express the gain of an RF amplifier. This is a difference between, let's say, electronics like op amps. Like for op amps, oftentimes you do express gains in voltage ratios. In RF, more often than not, the gains are expressed in dB, which is a power ratio. So if you have some kind of amplifier, you would express its gain in dB using P out versus P in like this. The gain in dB is 10 log base 10 power out over power in. Okay. So we'll talk more about that later. I want to give you some examples so you can think in dB and see why it's useful. But I've hit the wall on time for today. So don't forget, check out the homework assignments. There are 2 more left for the semester. Those are posted on Canvas along with their due dates and due times. Check Canvas for all the upcoming activities, assignments, labs, and lectures. I will hold office hours in just a few seconds. If you would like to stop by, please stop by. If not, I'll see you next time. Have a great night.